Okay, the next Physics 121 video. So in the last video, what we did is we talked about applying the Biot-Savart law, and it was a little bit of a challenging calculation because it involved cross product and some setting up integrals in a careful way. What we're going to try to do today is we're going to try to come up with something that was in some ways analogous to Gauss's law for electric fields, but we're going to develop Amperes law, which is going to give us a way to calculate magnetic fields for some important situations. Okay, so the start is to consider following some kind of arbitrary path through a magnetic field. So we're going to consider an arbitrary path from some initial point to some final point F through a magnetic field B. So let's just imagine some magnetic fields, and so I'll draw these magnetic field lines. The field doesn't have to be uniform, it could be changing, and so maybe it looks something like this, and we're going to follow some path from an initial point I, and we'll go to some final point F. Okay, so what I want to do is I want to divide this path into a bunch of short straight line segments. So these red arrows are going to approximate the curved green path, but they're going to be a bunch of short little sections that are straight. Okay, and so if I made the little red thing short enough, I could make my approximation to the curved green path as good as I want. So we divide the path into short straight line segments. And we're going to evaluate the following sum. So we're going to sum over I the magnetic field dot product with delta SI. And so what I mean by delta SI is that each one of these little red vectors represents a delta SI. So it's a vector of magnitude delta S, and it points in a direction that's tangent to the curved green path. Okay, so if we take the limit that sorry, I don't like that. Let's take the limit that delta SI goes to 0, then we could write this sum as the integral from an initial point to a final point of B dot ds. So this is called the line integral of the magnetic field B from some initial starting point to some final ending point. We've done calculations like this for the electric field. So for the electric field, when we calculated E dot ds, that told us the change in electric potential or the change in voltage, except there was just a minus sign in front of that. So we've done those types of calculations. So let's do this calculation for a special case. So, for example, let's consider this b dot ds for a closed loop path around a long straight wire. The reason we're choosing a long straight wire is because we know the magnetic field around a long straight wire from our Biot-Savart law calculation. So let's just recall, we're going to use it later, recall that for a long straight wire, we had found that B is equal to mu naught I over 2 pi d. So that was the magnitude of the magnetic field, and we know that it has a direction that encircles the long straight wire. So where d is the distance from the wire. So this is, I should say, this is a long straight wire with current I. Okay, so here's our long wire, and here is our current I. And what we're going to do is we're going to choose a path that goes around this wire that is circular, and it has a radius d. So let's choose a circular path of radius d with the wire at the center. Okay, so we know that the magnetic field is going to be circular as well, and so at some point on the path, the magnetic field direction is tangent to that circular path. And if we select a ds vector, so ds is a little segment in our circular path, and it's also going to be tangent to the green path. And so in that sense, the magnetic field and the ds, if we go around the path in, say, the counterclockwise direction, if we're looking from above, then ds and b are parallel. Okay, so we know that B encircles the wire. Therefore, B is parallel to ds for our chosen circular path. Okay, so when we calculate this line integral that we're trying to work out, then the b dot ds is just going to be b ds, since the cosine of theta would equal the cosine of 0 for parallel wires, or sorry, for parallel vectors, and cosine of 0 is 1. Okay, so that means when we evaluate b dot ds around our circular loop, that's going to be the integral of b ds. We've gotten rid of the dot product for parallel vectors. We also know that the magnitude of B is constant everywhere on the loop. Right, so every point on the loop is the same distance from the current, and for that reason, the strength of the magnetic field is not changing on the loop. So that means B is a constant. We can take it outside the integral. So this line integral that we're calculating becomes B, the integral around the loop of ds. But we did this exact integral for the current loop problem that we solved in the last video. The integral of just ds around a closed loop is the circumference of the loop. Circumference of the loop. And so that's just equal to 2 pi times the radius. We're using d for the radius of the loop in this problem. And so this line integral evaluates to b times 2 pi times the radius, or 2 pi d. Okay, now let's go back and use this result for the magnetic field strength due to a long straight wire. So it's mu naught I over 2 pi d. So B is mu naught I over 2 pi d, and then we multiply by 2 pi d, and what we find is that for our loop, we get B dot ds is just equal to mu naught times the current. And I'm going to put now a subscript on this thing. I'm going to say current through. So this is the notation the book uses. What this is going to indicate is this is the total current passing through our loop. What we're going to end up doing is we're going to call our loop an Amperian loop, where we get to choose the path that we're going to follow. Right? We started by saying, let's imagine we take some arbitrary path through some magnetic field. We're going to start for Amperes Law. We're going to choose those paths to be closed paths, and that closed path is going to be called an Amperian loop. And so this loop we'll refer to as an Amperian loop. Okay, this is Ampere's law, but we haven't done a general proof of this Ampere's law. What we've shown is a specific result for a specific case. We've imagined a circular loop with a current, a long straight current passing through the center of that circle. But let's just, for the sake of completeness, we'll call that Ampere's law. And what we're going to have to try to do is we're going to have to generalize it. And so I want to do the same problem, but we're going to choose a different kind of closed path around the current. So let's repeat this calculation for a different closed path surrounding a long straight current. So again, I'm going to be a bit careful about what kind of path that we work with. So let's imagine we have a current due to a wire that's coming straight out of the screen towards us. So the current is out of the screen. Okay, so what kind of path are we going to choose? I'm going to choose a path that, let me draw two, I'm going to try to draw two circular paths. So let me see if I can draw a better circular path. So I want a circle that is centered on this current. So that's just like the problem we just solved. Okay, let's accept that. And then we'll have a second circular path, again with the current at the center. Okay, so maybe this first circle has a radius of d1, let's say. So d1, and the second circle has a radius of d2. d2. Okay, and so what kind of path are we actually going to use? I'm going to use a path that, maybe I'll make the path a different color. I'm going to use a path that has a section along here, and then it's going to go perpendicularly between these loops, and then it's going to follow the smaller diameter circular path, and then it's going to have a perpendicular section again, and then it follows this kind of path along the outer circle, and then we come back in, and then we follow the small circle, and then we close it with another perpendicular section. Okay, good. And so if we were to draw the magnetic field at different points, along this path, we would say, okay, the current's coming out of the screen, so over here by the right-hand rule, the magnetic field is tangent to the big circle, and it's in this direction. And so over here, the field has a strength of B2. And over here on this arc, by the right-hand rule, the magnetic field is in this direction, and it's the same distance, D2, from the current carrying wire, and so that means that its magnitude is also B2. Okay, and then over here, what we've got is, let's see, current that would be coming out of the board, so magnetic field is pointing downwards here, and what's different now is that the strength is B1. It's closer to the current. B1 would have a stronger value than B2, and finally over here, this would be also a B1. Okay, let's do a couple more. Let's imagine what the magnetic field looks like over here. So the magnetic field is going to be always following a circular path. So let's just say this is some B, I don't know, BI. So I just care about its direction. Its strength would be between that of B1 and B2. In fact, what I should do is, B1's a stronger magnetic field. I should make these vectors longer than B2 if we want to have an accurate picture. So these vectors should be longer than the B2 vectors, and then these should be in between the B1 and B2 vectors. So we'll make B2 a little bit shorter. And so let's do one more over here. This is also going to be some kind of intermediate value between B1 and B2. So BI. Okay, good. And so for all of these little points, let's imagine we go around this path in a counterclockwise direction. And so over here, I would have like let's say a ds. I would have a ds vector in this direction. Over here, I would have ds in this direction, tangent to the path. This one's a bit different, right? Over here, we're going to stay tangent to the path, and so my ds vector is over here. Staying tangent to the path, I'm going to have a ds. Tangent to the path this time would be ds, would be in this direction, and ds would be in that direction. So I think I got all the little points where we labeled the magnetic field. Okay, so let's now think about trying to calculate this B dot ds around our closed path. Okay, so B dot ds, let's start over here. B and ds are parallel to each other. So for this first segment, we would have B dot ds is going to be equal to, well, this is B2, so it's going to be B2 ds because they're parallel. And what is the ds? And so let's do this integral of b ds. B2 is a constant from this part of the segment to this part, and so this is ds. When we did this for a circular loop, what we ended up with was the circumference of the loop, 2 pi times the radius. Over here, I don't have a full circle. I just have, let's say we labeled this as an angular displacement delta phi. So the length of this section is delta phi times the radius, and the radius is d2. So this becomes d2 times delta phi. So this is equal to b2 d2 delta phi. Okay, over here, we're going to get the same kind of result, but maybe this time the angle is, say, delta alpha. And so if for this segment we evaluated b2 dot ds, what we're going to end up with is b2 d2 delta alpha. Okay, what about the inner parts? What if we took this path? Then what we need to do is maybe label a new angle. Now, we're getting a little bit crowded here, but let's say that this purple angle is delta beta. Well, for this section, what we would get is the integral of b1 dot ds would be equal to, instead of b2, we'd get a b1. Instead of a radius d2, we would get a d1, and now the angle is delta beta. And finally, we have one more kind of section of a little arc, and from this one, we would get b1 dot ds would be equal to, well, we have to label another angle, and so this angle is, so we used alpha, beta, maybe we can use gamma. So that's delta gamma. Okay, b1 is constant on that little arc, and the integral of ds is going to be that arc length, which is the radius d1 times the angular displacement delta alpha. Okay, so that's B dot ds for all of the different circular segments, but we also have straight line segments. And so let's imagine this straight line segment here at the bottom left. So bi dot ds, well, that's just going to be 0 since bi is perpendicular to ds. And bi dot ds is bi ds cos theta. Theta is 90 degrees, and cosine of 90 degrees is 0. And so for all the straight line segments, what we're going to get is 0. And so if we label the different segments, like we would have segment 1, 2, 3, 4, 5, 6, 7, we have 8 different segments. And so this B dot ds around the closed path is B dot ds around segment 1, and yes, I'm going to write this out 8 times. 2, 3, 4, plus 5, plus 6, plus 7, and plus 8. Okay, which ones are straight line segments? 2, 4, 6, and 8. All of the straight line segments contribute nothing. 2, 4, 6, and 8. So the straight line segments contribute nothing to the B dot ds around our closed path. So that means, what are we left with? We're left with the sections on these circular arcs. And so we have 1, 3, 5, and 7, but we worked them all out already. 1 is B2D2 delta alpha. So it's B2D2 delta alpha. 3 is B1D1 delta beta. And 5 is B2D2 delta phi. And 7 is B1D1 delta gamma. Okay, now for a long straight wire, or let's say a long straight current, we know that B is equal to, let's just remind ourselves what that was. It was mu naught I over 2 pi times D. So the B1s have a D1 and the B2s have a D2. And so that means B times D is just mu naught I over 2 pi. And so whether it's B1 D1 or B2 D2, that product is always just mu naught I over 2 pi. And so if we put that in, our integral around a closed path is B dot ds is equal to B times D is mu naught I over 2 pi. And we're going to get that for all four of our terms. And then we're going to get a plus delta alpha plus delta beta plus delta phi plus delta gamma. Let's go back and look at our picture though. And if we add up delta alpha, delta beta, delta phi, delta gamma, then we go all the way around our current carrying wire, and this sum of angular displacements is 2 pi radians for a complete loop. And so therefore what we end up with is B dot ds is equal to mu naught I. The 2 pi's cancel, and what we'll do is we'll put our subscript back on that this is I through. So we've gotten the same result twice now. Amperes Law. We got it once for a circular path, and we've got it now a second time for a path made out of circular sections and straight line sections that are perpendicular to those circular arcs. What you could do is you could imagine taking any arbitrary path around a long straight wire, for example, and dividing that path into little circular sections and little straight line sections. And for all the circular sections, you would get the types of results that we wrote down for our sections 1, 3, 5, and 7. And when you added them all up, all the angular displacements would cancel, would add up to 2 pi, and they'd cancel with the 1 over 2 pi that we had for the current of a long straight wire. All of the straight line sections would contribute nothing. And so this result holds generally for any path around our current. So Amperes Law holds for any path surrounding a current. Okay, let's do one more thing. Let's imagine that we take a path in the vicinity of a current I from, say, a long straight wire. And we just choose a path that's a closed loop path but doesn't enclose the wire at all. So what about a closed loop path? Here, let's rephrase this. What about a closed path that does not surround the current? Okay, so let's take a current coming out of the page. Maybe it's a long straight wire again. And we'll draw concentric circles again. So there's one of a radius, say, d1, and here's another one of a radius d2. Okay, this time our path is going to be an arc on d1, and then we'll take a perpendicular out to d2, but this time we're going to take the arc and we're going to make a closed path like this. So it is a closed path. Maybe we'll go and we'll traverse this path in the direction shown here. Okay, so we can do this thing where we say, all right, if the current I is coming out of the screen, then we could draw magnetic field vectors. Let's see. The magnetic field at this point would be in this direction, say B1. And then over here, it's in the same direction. It's just a little bit of a weaker magnetic field because we're further away from the wire. And then over here, we have something in between those two, and I think we call those BIs. And over here, we have another BI. All right, and then we have delta S vectors, or DS vectors, DS, DS, and here we're going DS, and over here we're going this way, DS. Let's label one angle here. This is going to be a little bit easier than the other one. And we'll say that this angle is, say, delta phi. Okay. For the inner circular path, we don't have to redo all these calculations. We did them already in the case above. So the B1.ds is going to end up being B1 D1 delta phi, exactly like we did above. For the outer circular path, we're going to have a B2.ds. It's going to be similar to what we calculated before. We'll get a B2 D2. The angle is delta phi. The only difference is now the magnetic field B2 and the displacement element ds are anti-parallel. So when we evaluate the dot product, we're going to get the cosine of 180 degrees, which is going to be a -1. So we'll pick up a minus sign here. And bi.ds is equal to 0 for the straight line paths. So that when we add up all the contributions, so for our closed path, this is the closed path that doesn't surround any current, right? This b.ds is going to be, we're going to get a b1 d1 delta phi, and then we're going to get a minus b2 d2 delta phi. And, well, the b1 d1, remember, is mu naught I over 2 pi, and then we get a delta phi. b2 d2 is also mu naught I over 2 pi. Then we have the same delta phi, and so those equal to 0. We could also express this as, let me write it on the next page. We could express this as b.ds around a closed path, and we could still say that that's mu naught I through. It's just that for the path that we examined in this particular case, the current through the path is 0. The current is only flowing at some point outside of the path. And so we could say for the current case, maybe current is not, let's say for the present case, I through is equal to 0, therefore Ampere's law is still valid. Okay, what we'll do in the next video is we'll think of some applications of Ampere's law. In particular, we're going to consider the important case of a solenoid and see if we could calculate the magnetic field due to a solenoid, which is going to be a coil of wire. So we're going to take a long wire, we're going to coil it up so that it's like a slinky. We'll pass a current through it, and we'll see if we could calculate the magnetic field in the vicinity of that coil of wire. All right, thanks very much, and we'll talk to you next time.